Hello, math friends. This is Precalculus, section 3.5 notes. Today we're going to be discussing complex zeros of a polynomial. We're going to begin with the fundamental theorem of algebra. And the fundamental theorem of algebra has a very fancy name, but it's basically something that intuitively we all already know. And this is that every polynomial has at least one complex zero. And a polynomial of degree n has n complex zeros. Now I know what you're thinking. You're thinking, wait a minute, that's not true. A lot of polynomials have all real solutions, but recall that all real numbers can be expressed as complex. It's just that the complex part of the number is zero. All right, so for our first example, they ask us to find all zeros of P of X, both real and complex. Well, before we even begin, we should know how many answers we are looking for, okay? We are looking for 3 because this is a degree 3. At this point, we don't know of those 3 how many are real and how many are complex. However, we do know that complex solutions always come in pairs. So either we're going to have 3 real zeros or we're going to have 1 real and 2 complex, or 1 real and 2 imaginary, okay? The first thing I notice is I have 4 terms, and it looks to me as though this polynomial can be factored by grouping right away. So that's where I'm going to start. I'm going to pull an x squared out of the first 2. That's going to leave me with x minus 5 in the parenthesis, and I know that I have to have x minus 5 in the second parenthesis as well, positive 2 in the front. So this leaves me with x squared plus 2, the binomial, and x minus 5. Okay, now I'm not done, but I'm a heck of a lot closer to being solved. I can go ahead and just replace that p of x with 0 on the other side of the equal sign, and now I can use the zero product property to solve. So I can say x squared plus 2 has to equal 0, and x minus 5 has to equal 0. Well, the x minus 5 part is real. That when we add 5 to both sides, this just gives us a solution of x equals 5, which we know is a real, non-imaginary solution. Again, we could call it complex. All solutions are complex technically, but this is a real versus an imaginary solution. Now over here, when I solve for x squared, I'm going to subtract 2 from both sides. This is going to give me x squared equals negative 2. And then when I square root both sides, I'm going to get x equals plus or minus, and the square root of negative 2, I am going to express as x equals plus or minus I square roots of 2. And of course, these two solutions are going to be imaginary solutions. So I've found all of my solutions. There were 3 of them. 1 of them was real, and 2 were imaginary. The complete factorization theorem says that if p of x is a polynomial of degree n, which is greater than or equal to 1, then there exists complex numbers representing the zeros of p of x such that we can write p of x in factored form. It's just that some of our factors may have complex zeros in them instead of real zeros. So if we use the results from the above example, remember that the zeros that we just found from our last example were x equals positive I square roots of 2, negative I square roots of 2, and of course 5. So if we wanted to, we could go ahead and we could write p of x in factored form. Looks a little silly, but we could say p of x is equal to, remember, factors are always opposite of solutions. So this solution would come from the factor x minus I square roots of 2. this solution would come from the factor x plus I, square roots of 2. And then this would come from the factor x minus 5. So this would be how we would rewrite the polynomial p of x using the complete factorization theorem. So now it's time to talk about zeros and their multiplicities. So we have a polynomial here that is degree 4, and somebody has gone and factored it for us, which is lovely. So we can see that we're going to have, based on the factorization, we're going to have 3 different zeros. That monomial x squared is going to give us a 0, or a solution of x equals 0, and that has a multiplicity of 2, meaning it's a 0 2 times. Then we're going to have x equals negative 2i and x equals positive 2i as the other solutions. Again, I'm getting these from the polynomial. This one gives me x equals 0, this one gives me x equals negative 2i, and this one gives me x equals positive 2i. And these two imaginary solutions have a multiplicity of 1. And the total number of zeros is 4, again, because the degree of our polynomial is 4. That should always match. Okay, in the next example, we have a polynomial with a degree of 7 that's been factored for us. But we only have 3 unique factors, which means that each of our zeros has a multiplicity greater than 1. So this factor right here, x minus 2, gives us a solution of x equals 2. But since that factor is to the 3rd power, that tells us that the multiplicity of this 0 is 3. X equals 2 is a 0 3 times for this polynomial. The x minus 6i factor gives us a solution of x equals positive 6i. And because it's squared, this 0 has a multiplicity equal to 2. And then the 3rd factor, x plus 6i, gives us a solution of negative 6i if we set it equal to 0. And since that factor is squared, that also has a multiplicity equal to 2. So if we count all these up, 1, 2, 3, 4, 5, 6, 7. So once again, the degree of our polynomial and the total number of zeros that we have match. In the next example, we want to factor the polynomial completely and find all of its zeros. And then after that, we're going to state the multiplicity of each 0. Okay? And we're going to do this by first finding all of the factors of the polynomial. And I don't think I have enough room on this page to complete this problem, so I'm going to go ahead and extend to the next page. So my polynomial is p of x equals x to the 5th plus 8x cubed plus 16x. So if I'm going to start by finding all the factors of this polynomial, the first thing I'm going to do is pull out the GCF of x. So this is going to look like x times x to the 4th plus 8x squared plus 16. And now that I've done that, what I have here is an easy factor. A is 1. Remember, you can factor 4th degree polynomials as easy as you can factor 2nd degree polynomials. The rules are the same as long as you have an x to the 4th, an x squared, and a constant. So this is an easy factor. I'm looking for 2 numbers that multiply to make 16 and add to make 8. So that's going to be positive 4 and positive 4. So this is going to become x times x squared plus 4 times x squared plus 4. So now my factoring is done, okay? And I could rewrite it like this. I could write it as x times x squared plus 4 squared, right? Because that x squared plus 4 is a repeating factor. It occurs twice. This right here, this GCF of x, gives me x equals 0 as a solution. And of course, this solution has a multiplicity of 1. The x squared minus 4 equals 0 occurs twice. When I set this equal to 0, x squared plus 4. When I set that equal to 0, I'm going to subtract 4. So I'm going to get x squared equals negative 4. And then when I square root both sides, I get x equals plus or minus square root of 4 is 2 and square root of negative 1 is I. So I get x equals plus or minus 2I. Now since this factor is repeated twice, this is two solutions here, but they both have a multiplicity equal to 2. So that means positive 2I is a solution twice, and negative 2I is a solution twice. Now the problem asked me to factor the polynomial completely, find all of its zeros. Okay? By the complete factorization theorem, we can rewrite this polynomial using its solutions in its complete factored form. So this would be p of x equal, we'd have that x on the outside, but then if our two solutions are positive 2i and negative 2i, we could write these factors as x minus 2i. That would be the factor that positive 2i comes from. And again, it's a solution twice, so it's squared. And then x plus 2i would be the factor that the solution negative 2i comes from. And again, that's going to be squared. So if we count up our exponents here, we have a total of 5, and our original polynomial had a degree of 5. In the next polynomial, it says factor completely and find all of its zeros. Well, I'd sure like to factor it. X squared minus 6x plus 10 looks like it's going to be an easy factor, but you quickly discover that with the factors of 10 being 1 times 10 and 2 times 5, there's no way to get negative 6 out of that. So since this can't be factored, we're going to find the zeros by the quadratic formula. Okay, so I'm going to do the quadratic formula right away. I'm going to plug in my a and b and c. So x is going to be equal to the opposite of negative 6, which is 6, plus or minus the square root of b squared. That's going to be negative 6 squared, plus negative 4 times a, which is 1, times c, which is 10. And this is all over 2 times a, which is 1. So then if I simplify this, I get 6 plus or minus the square root of negative 6 squared gives me positive 36. Negative 4 times 1 times 10 is a negative 40. And this is all over 2. Continuing to simplify, 6 plus or minus. Under the radical, 36 plus negative 40 gives me the square root of negative 4 over 2. Square root of negative 4 can be simplified to 2i. So I have 6 plus or minus 2i over 2. And then again, since I have all even numbers here, the 6 and the 2 and the 2 can all be divided by 2. So I end up with 3 plus or minus 1i divided by 1, or just 3 plus or minus I. Okay, so keep in mind, this is really two solutions. This is x equals 3 plus I, and this is x equals 3 minus I. It's important to make that distinction because our next job is to use the complete factorization theorem to write this in its completely factored form. So our polynomial p of x is going to be written as, and we're going to do this in 2 steps. It's going to be x minus, because it's always x minus the solution for the factor. So it's going to be x minus 3 plus I, and that's going to be x minus 3 minus I. Notice how I'm doing nested parentheses. So then I'm going to go ahead and I'm going to distribute that negative sign and get rid of the inner parentheses. So my final answer is going to be p of x equals x minus 3 minus I times x